طيب بسم الله الرحمن الرحيم. We have here in section 2.7 a simple application on computer graphics, how to do animation using matrix multiplication. Okay, these are samples of some computer graphics software such as 3D Max, Blender, SolidWorks, and so on. As you see here in the graph, you see some points are translated, some are rotated, and so on. Would like to know how to do this using matrix multiplication. Let's first introduce what is called wired frame object. Assume that I define the letter N through the coordinates of the vertices of the letter N. So I'll take the coordinates of vertex 1, 2, 3, 4, and 5, and so on to draw the letter N. This might be something like this, a matrix containing the coordinates of the vertices. Assume that here is the origin, and this is the second vertex, and so on. So this is how you can graph the letter N. We're going to do now some transformation on the object through matrix multiplication. So define this process that you are transforming the vector x to a new vector according to multiplying the vector x by a certain matrix. So for example, assume that I am going to multiply each vertex by this matrix. So you are going to multiply this matrix by the first vertex, second vertex, and so on. If you want to see the effect of this guy, assume that you have a vector x and y multiplied by the matrix 1, 0.25, 0, 1. So what would be the output? Multiply, do the multiplication. So we'll get x plus 0.25y and y. So y is not going to change, but x, you add to x some portion of your y. Okay, let's see if you multiply this by the whole vertices. So we can multiply it at once. Multiply the matrix A by matrix containing the vertices, and you get something like this. So as you note here, the y as it is, but x increased somehow by taking a portion of your y. If you try to graph the new vertices, let's look at the output. So what happened? The x for the vertices, for some vertices are changed, increased. Okay. So if this guy is a regular letter N, so this guy could be the italic letter N. So you can get the italic by this transformation, for example. This effect actually is called horizontal shear. Okay, we define this guy as horizontal shear. Assume that I'm going to do the same, but then I want to scale the vertices such that x is scaled about 0.75. So how to write a matrix that scales x by 0.75? What to write here to get this effect scaling in x direction? So I write here 0.75, 0, 0, 1. So if you multiply, you'll get this guy. So this guy is scaling x by 0.75. Okay, assume this matrix is S, scaling. So we can apply the two transformation, the one that does the horizontal shear, and then the one that does the scaling. So we can multiply the two matrices together. This guy for the horizontal shear, and this guy for the scaling along x direction. So if you multiply this guy, you will get what is called the composite transformation that does the both effects. So for example, if this is your letter n and you apply this transformation, you get this guy. If you then do scaling for the letter n in x direction by 0.75, you will get this letter n, which is somehow narrower than this one. Okay, so this product you can apply directly on the letter n to get this transformation. Okay, this is because when you do the shear effect, the letter gets wider. So you can then scale it again in x direction to be in the same size as the original n. Okay. Okay. Now assume that I want to do a translation. I want to shift in x direction and in y direction. Assume that I want to change x by adding 1 and y by adding 2. Can you write here a matrix that does this transformation? Matrix multiplication that is independent on x and y. I want to do it for all the vertices. So this guy must be constant. Can you do this through matrix multiplication to get this guy? You can't, right? Can you? However, if you use something called the homogeneous coordinates, we can add to our vector a third dimension called 1. Okay? Can you do it this way? X plus 1, y plus 2, and 1. Can you do it this way? So we write here 1, 0, 1, and then 0, 1, 2, then 0, 0, 1. So actually we are going to use these coordinates, which is called the homogeneous coordinates. So we move our objects from 2D to 3D by adding 1 in the third dimension. For this reason only, to do the shift or translation using also matrix multiplication. Okay? So we're moving from R2 to R3. So 0 and 0 becomes 0, 0, and 1. Okay? We are not going to add or do scalar multiplication. We only use matrix multiplication. Okay? So in general, to do the translation to x plus h and y plus k, so this guy would be h, and this guy would be k. All right? So if you have this is the original object and you want to translate it to this place, so you have to do translation in x by 2, translation in x by 4. You take this point at x equal negative 2 and this point at x equal 2. So you move, shift x by 4. And if this is 1, you are going to shift y by 3. Okay. And what about the horizontal shear? How to write a horizontal shear? The matrix for horizontal shear, if you remember, you add for x, I want to add a portion of y, right? So the matrix would be, you have x, y, and 1. I want here, for example, x plus ky, y, and 1. So what are the values for the transformation matrix? 1, k, 0, 0, 1, 0. So I prefer to write this first and then write the matrix. Okay? نعم كده horizontal shear. If this is the original object, this is the sheared object in horizontal. You sheared the object in the horizontal direction. اللي فوق translation. This is a translation by h and k, and h is 4 and k is 3. What happened here? What is the transformation? If this is the original object and this is the transformed one, ده vertical shear مش كده؟ طب تعرف تقول لي بقى الماتريكس؟ Let's write here the effect first. What happened to x as it is? X as it is. What about y? You added a portion of x to y. How much do you add to y? For example, this point, 1 on 1, becomes 1 and 3. So you add it to this one, the original y, 2 times the original x. 2 times x. Right? Then write the matrix. So matrix 1, 0, 0, 2, 1, 0, 0, 0, 1. Okay? Is it simple? Okay. This is not shift. Shift, you find the object is moved to this place. But this is not shift. You just shear the object this way. What happened here in this object? Scale down by
2 in x direction and 2 in y direction.
So x becomes x becomes
plus 2y minus 2y. هيبقى x plus multiple من ال y.
This is the original x, and this is the transformed x. Okay, so what happened? Over 2, scaling you multiply, not subtract. Subtract means that you shift. You are not shifting. So x is scaled down by 2, and y, right? So you'll have here half, 0, 0, 0, 1/3, 0, 0, 0, 1. Right? So in general, scaling by s and t, you will find s and t on the diagonal. What happened here? This is the original object. Okay? And look at the points. This point is transformed to this point. This point to this point. So what we did actually, is it shift? Translation? Reflection? Reflection. Reflection. So what happened to x and y? X would be negative x and the same y. So what to write here? Negative 1, 0, 0, 1. Okay? So this is the shift about y-axis. You change the x. Do you remember the even function? It has to do with the even function. Replace x by negative x. So what happened here? This is the original object, and this is the transformed one. You are reflecting about y equal x. So What about these guys? What to write here? 1. Y and x. You switch y and x. So what is the matrix?
0, 1, 1, 0.
Right? Do you remember the inverse function? You have a symmetry about y equal x, and you change x and y to get the inverse function, right? What about reflection about the origin? Reflection about the origin. So what happens to x and y? Instead of x, you'll get negative x. Instead of y, you get negative y. So you'll have negative x and negative y, right? So here negative 1, 0, 0, negative 1. Like this guy. This is the original object. So this point is transformed to this point. You change the sign of x, I change the sign of y. What about this guy? This is the original object, and this is the transformed one. Reflection about y equal negative x. So what happens here to y and x? You change x and y, and they change their signs as well. You'll get x and y changed, and the sign changed, right? For example, if you want to see it, if this point is negative 2 and 1, it would be transformed to this point, which is negative 1 and 2. So x and y changed, and they changed their sign. What about rotation? We need to do some rotation for the object about the origin by angle phi counterclockwise. The simplest way is to do this through, if you remember, the polar coordinates. So if this is the original point, x and y, you will have here r and angle theta. If you do rotation by angle phi, you will get the same r, but the angle would be theta plus phi. So this is the original x and y, this is the transformed one. Let's try to write the transformed point in terms of the original point and the angle phi. So we have x in polar coordinates equal r cosine theta, and y equal r sine theta. What about the new x and y? X prime would be r, the same r, cosine theta plus phi. You can expand this, right, using the trig identities. So this guy is r cosine cosine plus or minus sine sine. So what do we get actually here? R cosine theta, which is the original x, multiplied by cosine phi. And then r sine theta, which is y sine phi. And do the same for y prime. What about y prime? R sine theta plus phi, which is r sine cosine plus cosine sine, and you'll have here r sine theta, which is y, cosine phi, plus x sine phi. So now I have the new x and y in terms of the original x and y. So can you write the transformation matrix? So what would be the transformation matrix? You can read it from x prime. You have x cosine phi minus y sine phi. So we'll have in the first row cosine phi, then negative sine phi. In the second row, we'll have sine phi, and then cosine phi. Something like this. So this guy is for the rotation counterclockwise by angle phi to get the new x and y. So can we do a composite transformations that perform the following operations? I want to write it in homogeneous coordinates, 3 by 3 matrix, correspond to scaling by 0.3. If you don't say scaling in x or in y, you do both. So we have here scaling in x and y by 0.3. And the default rotation is about the origin and counterclockwise. Okay? Here I said counterclockwise by 90 degrees. And then I want to do translation that adds negative 0.5 to x and 2 to y. So let's do it step by step. The first transformation to scale x and y by 0.3. So what is the matrix? 0.3, 0, 0, 0.3, 0, 0, 0, 1. So if this is the original object, you will do some scaling in x and y to get the new object. So it is scaled something like this. مش باينة صح؟ طب عايزين نعمل بقى transformation counter clockwise by angle 90 degrees. ادي هي ايه؟ الماتريكس قلنا cosine phi negative sine and then sine cosine. يعني نكتبها هنا كده. يبقى cosine negative sine sine cosine. So for phi equal 90 degrees, you will get here 0, negative 1, 1, 0. All right? So this is the second effect. So first you scale and then rotate your object by 90 degrees counterclockwise. The third effect, to do the translation in x by negative 0.5, y by 2. So the transformation matrix is 0, 0, negative 0.5, then 0, 0, 0, 0, 1. مش كده؟ الأولاني 1, 0, negative 0.5, 0, 1, 2, 0, 0, 1. Right? How to write the composite transformation? You multiply the three matrices. In which order بقى؟ T1 to 3 ولا T3 T2 T1؟ مش هتفرق. T3 to T2 1. Because this guy is going to be applied first on your object here. Okay, your vector is written here actually, so T1 is the first effect, then T2, then T3.
الساين اوبريشن اللي انا بعملها دي اصلا اندبندنت على الشيء بتاعي.
بس في بعض الاوبريشنز هتلاقيها يفرق معاك الاوردر زي الاكزامبل ده.
هو انا لو بروتيت مثلا حوالين بوينت فماشي. يعني لو بروتيت حوالين مثلا فيرتكس في المثلث بتاعي هتفرق. انما انا ان جنرال لو انا
مش عارف هي مش باينه بس يعني هنا ده الاوريجينال اوبجكت and then scaling and then rotate. هل كان ممكن أعمل rotation, scaling, في translation أو المشكلة هتجيلك في translation، لأن أنت ممكن تعمل translation هنا للأوبجكت وبعدين تعمل روتيشن هيبقى كده، ده في حتة تانية خالص. هو الترانسليشن هو اللي هيبقى بروبلم عنه، فهنا البروبلم دي هيفرق مع الاوردر اوف اوبريشنز. عشان كده انت be careful to write it this way, first effect then second and third to do it correctly. So is it simple the animation? Okay, let's see some example on MATLAB. So assume that I want to graph the letter N that I graphed first and then make it italic and then resize it. So these are the coordinates of the vertices of the letter N. This is the first row, the X position, and then the Y row, and then 0 for the third dimension. The first row, second row, sorry, 1 for the third dimension. اللي هي نكتبها in homogeneous coordinates. And then I'm going to plot X and Y. So by default, MATLAB connects the point, every point to its adjacent point. And this axis to set the limits of the axes and then pause to wait for a key to be pressed. So let's run this guy. مش عارف باينة ولا لأ؟ وده كده المفروض الليتر N بتاعنا. بعد كده let's do the transformation. احنا قلنا هنعمل transformation اللي هو shear effect اللي هو كان X added ليها 0.205 from Y. Okay, so this is the horizontal shear in homogeneous coordinates, and then multiply T by X and replace it by the old X, and then plot again and pause. So let's do it here. So we'll get here the italic N. And then the last transformation is to do the scaling. So this is the scaling in X by 0.75. And again T by X to get the new X and so on. Okay. Yeah. Let's see some other effects. What happens to this star? Assume that this is the origin, so it is rotating about the origin. What about this one?
Reflecting about لا بتروتيت على الاكس اكسس. ماشي عليك.
This is actually the effect of rolling. You are rolling the star. How to do it? So you have some translation and some rotation. So this is done actually in 3 steps. You translate and then rotate and then translate the origin back. Actually what we did in this rotation is rotation about the origin. If you are not rotating about the origin, about certain point here, you have to make this point first the origin and then do the rotation and translate back to the original origin. So it's done through 3 steps. Okay?
هو في الروتيشن ده كان في اكسس يعني في فيرتيس من الشيب على الاوريجن لو هي بعيده.
Doesn't matter. If you are going to have here the origin and you are going to rotate the object like the star. So this is the original R, and after rotation this is the same R, and the angle is increased by the angle phi. But if you are going to rotate about certain point here, the object about certain point, you have to make this point first the origin to apply this rotation. تعمل translation أول, then rotation, and then translation back. Right. Let's have a break 10 minutes. Okay. And then get back to section 2.8. Bismillah ar-Rahman ar-Rahim. In section 2.8, we are going to define what is called a subspace of Rn. So actually, we are going to take some part of Rn. This is Rn. I'll take some part of Rn and define this part to be what is called subspace if it satisfies certain conditions. Okay, this is a subset. So for example, H. So H is a subset from Rn. If it satisfies some conditions, I will call it subspace. Okay. Actually, these conditions are simply that you can do linear combination between any vectors in this subset without going outside the subset. We'll say it short. And then define some well-known subspaces for the matrix called column space, null space, and row space. And for each subspace, we'll get what is called the basis for the subspace. This is about section 2.8. And 2.9 is related to this guy to find what is called dimension of the subspace and rank of a matrix. So today let's take 2.8 first. This is the formal definition of the subspace in Rn. A subspace of Rn is a subset H of Rn that is closed under addition and scalar multiplication. So what do you mean by that? If you take two vectors inside H, vector u for example and vector v, I have to guarantee that the sum still inside H. If the sum is inside H, we say that H is closed under addition. And when you do scalar multiplication, if you scale this vector, you find the scaled one is also in H. So we say that is closed under scalar multiplication. If it satisfies both conditions, we say that the subset H is a subspace of Rn. Okay? So this condition, take U and V inside H, okay? And you want to guarantee that the sum is inside H. And if you do scalar multiplication, okay. If you put here, for example, C equal to 0, you will get 0 vector. So the 0 vector must be inside H. So some texts write it as a condition that you have to find the 0 vector inside your subset. And if it satisfies this condition, we say that the subset is a subspace of Rn. So let's see an example. If you take any straight line passing the origin and check if it is a subspace of R2 or not. If it is passing through the origin, then the 0 belongs to the line. So it satisfies the first condition. What about if you take two vectors on the line? You have a certain line in R2. Okay, passing through the origin. If you took two vectors here and sum these two vectors, then the sum would be on the same line, right? And if you scale multiple the vector, if you scale multiple, you will find also that the scale multiple is on the line. So the straight line that passing through the origin We can call it a subspace in R2. What about line not passing the origin? Could it be a subspace? It has a problem of 0. The 0 vector is not on the line. So the 0 is not on the line. And also if you take two vectors on the line, then the sum would not be on the line. So it doesn't satisfy any condition actually. If you scale multiple the vector, you will get a vector outside the line. So this is not a subspace of R2. What about plane passing through the origin in R3? Plane passing through the origin in R3. If you remember, the plane in R3 can be spanned by two linearly independent vectors. In R3, any plane in R3 can be spanned by two linearly independent vectors in R3. If you look at this example, if you have U and V linearly independent, so they can span this whole plane. So does this plane satisfy the condition for a subspace? The 0 vector on the plane, right? And if you add two vectors, the sum would be on the plane. And scale multiple would be on the plane. So this plane is a subspace in R3. Actually, if you look at this expression for the span, if you put the C is equal to 0, so we guarantee that the 0 in the plane. If you put C1 and C2 equal to 1, so we guarantee that the sum inside the plane. If you put C2 equal to 0, so the scale multiple of U inside the plane. So actually any span would be a subspace. Okay. And this is what we have to satisfy for defining a subspace. You have to guarantee that the linear combination of vectors remains on the plane. Okay. So what about this guy? Could it be a subspace? You take all the vectors in this form, x1 and x2, such that x1 is greater than or equal to 0. So this is x1 and x2. So actually, what is this part in R2? The right half plane, right? This part, right? Does this satisfy the condition of the subspace? You find the 0 on the subset H. If you take two vectors in H, would the sum be in H? Sum هيبقى in H برضه مش كده؟ What about scale multiple? Not every scale multiple. I have to guarantee that all scale multiple for any C's. If you have negative, for example, you will get outside. So the 0 exists. It is closed under addition, but it's not closed under scalar multiplication. So this is not a subspace. Actually, what are the possible subspaces in R2? If you get back to the spans, you can get the answer directly. All possible subspaces in R2. Line passing through the origin. The whole R2. As a special case, the 0 vector. Okay? Would satisfy the condition for a subspace. What about R3? What are the possible subspaces, which was previously said as possible spans? Plane passing through the origin in R3, line passing through the origin with 0 vector, and the whole R3. Okay. ما احنا قلنا لازم الاوريجين يبقى in the set to be subspace. This is a condition. مش احنا قلنا عايزين satisfy conditions دي ان C1 U تبقى belong to H if U belong to H. عايزة guaranteed for all C's. One of the C's would be 0. So I have to guarantee that the 0 is inside H. So this is what we said, that if you have certain vectors, then directly the span of the vectors is a subspace. Okay? You don't have to do anything. Say that this is a span of vectors and consequently it satisfies the conditions of the subspace. So let's define some well-known subspaces for a matrix. The first one called the column space of a matrix. The column space denoted by col A, okay, is defined to be all the vectors spanned by the columns of A. So for example, if this is the matrix A, written in terms of its columns, we say that the column space is the span of the columns of the matrix A. So is this a subspace? Is this a subspace? A subspace. Why it is a subspace? Span, because it is a span of some vectors. What about the row space of a matrix? It would be the span of the rows of the matrix, okay, and denoted by row A. So if you have a matrix A m by n, you have a matrix m by n, what you can say about the column space? The column space would be a subspace of which space? The columns D belong to R M, right? Rows belong to R N. So the column space would be a subspace of Rm, and the row space is a subspace of Rn. If you remember, when you solve the problem of a system of equations, Ax equal b, we said that you can write it this way in terms of the columns of A and the component of the x, and we said that b can be written as linear combination of the columns of A if you find a solution for your problem. So we said that you find a solution if b can be represented as linear combination of columns of A. We add another word today that you say that you find a solution if b belongs to the column space of A. Column space is the span of the columns. So the system is consistent if b belongs to the column space of A. So if I ask you to determine if b belongs to the column space of A, so as before, you simply do the reduction. Okay. So assume that we got this matrix after reduction. So do you have a solution? We have a solution, which means that b belongs to the column space of A. What does the column space represent in this example geometrically? Is it the whole R3 or subspace of R3? Plane in R3. How do you know that it is a plane? Number of pivots, 2. Then you have 2 actually linearly independent columns in the matrix, so they span a plane in R3. So if this is the column space, so you'll find here B in the column space, and then you have a solution. The null space of a matrix, we define the column space and row space. Let's define the null space. The null space is defined to be all the solutions of the equations ax equal to 0. So all the x's that satisfy this equation is a subset of Rn, okay? And we'll show that this subset is a subspace called the null space. So assume that I want to find the null space of this matrix. So I'll solve the problem ax equal to 0, right? So then you'll do the reduction. And after reduction, you'll get this matrix. And let's read the solution vector. I have one equation after reduction, 10x1 minus 3x2 minus 2x3 equal to 0. Do you remember? And then we write the pivot variables subject to the free variables. We have x2 and x3 free. And this guy is the pivot variables. So x1 equal
0.3 minus 2, 0.2 minus 3.
Can you write it in vector 4? X equal the free variables times vectors, right? So x1 is 0.3 x2 and 0.2 x3, and x2 1 0, x3 0 1. This guy is called the null space of the matrix A. Why it is a subspace? This is a subspace of R3. Why it is a subspace? Now look at this guy. It is the span. It is a span. So since it is a span, then it is directly a subspace. This is a span of actually two linearly independent vectors. So the span of these guys is a plane in R3. Okay. So let's write it in a rigorous form, how to prove that the null space is a subspace. To be a subspace, you have to satisfy all the condition of the subspace. If you remember, the null space is given by this equation. So first, does the 0 vector satisfy this equation? You put 0 here, it would satisfy. So the 0 belongs to the null space. What happens if you have two vectors belong to the null space? Does the sum belong to the null space? Is this guy would be 0 from the distribution, right? And the same for the scalar multiplication. So this is how to write the proof that the null space is a subspace. The 0 vector belongs to the null space. If you have two vectors in the null space, then the sum belongs to the null space. This is the addition closure. If you have vector belong to the null space, if you have scalar multiple, it would also be in the subset. So it is a subspace. Okay, so we defined actually the column space, the row space, and the null space of a matrix. So let's find for each subspace what is called the basis for the subspace. Do you know what is the basis of the subspace or for any space? Basis of R3, Ij, and K, right? These are actually the standard basis for R3. So what are the conditions for a set to be a basis? It has to satisfy two conditions. It has to be linearly independent vectors and can span your space. So if you have a vector that span your subspace H and they are linearly independent, I call it a basis for this subspace. So as you said, the standard basis for R3 IJK, because they are linearly independent and they span the whole R3.
سؤال لوحده مش بيسبان R3
مين اللي لوحده؟
يعني
احنا بنقول السيت اوف فيكتورز the three vectors.
انا مش هتكلم على فيكتور.
The three vectors can span R3 and they are linearly independent. This is the problem I solved here for the null space. Can you find a basis for the null space from here? This is the null space. Can you find a basis for this subspace?
0 1 0 1 0 1. Okay.
Take these guys.
انا بتكلم ال 0.2 ده يعني
This span your null space and they are linearly independent. So these guys are actually the basis for the null space. So simply when you write the null space in vector form, you will get directly the basis of the null space. Okay. Let's try to find the basis for the column space of A and B. Let's do it first by inspection and then find a way to get the basis for the column space. By inspection, can you find any relation between the columns of the matrix A? Look at the matrix A. Do you have any relation between the columns? No relation between the columns.
يعني ده بيساوي ده زائد ده
So
بيساوي
let's say it in mathematics. A3, the third column,
A1 plus A2
equal A1 plus A2. And A4 equal A2 plus A3. So if I ask you to find a basis for the column space, which means that I want to find linearly independent columns that can span your columns. So what do you suggest to get, to be the basis for this matrix?
ممكن اديوس بقدر الامكان بس هي
Take A1, A2, A3 is a linear combination of 1 and 2. ممكن ناخد A1 و A3 أو A2 A1 and A2 and خلي بالك A5 ده لازم تاخده ولا في 6 هنا، ده الوحيد اللي عنده هنا 6. فدول كده ممكن يبقوا بيزس، ده كده بيزس for column space of A. طب let's do the same for the matrix B. Do you have any relation again between the columns?
the same A1 plus A2 equal A3.
Let's write it in B. So we'll have B3, B1 plus B2,
B4 equal
the same relation, right? So let's do the reduction for the matrix B and see what we get. If we do the reduction, what do we get for the matrix B? Take the first one as pivot and then subtract. So we'll get 1, 2, 3, 5, 0, 0, 2, 2, 4, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 6. Right? So what about the basis for the column space of B? Which columns to take as the basis for the column space?
B1 or B2
B1 and B2 and B5.
طالما وصلت لنفس الكومباينيشن بين السبيس ده فانا
طيب
لازم اوصل لنفس
Did you notice بقى anything about A and B? بص على relations دي, they are the same as this guy, which means that the row reduction preserve the relation between columns. This is a very interesting property. When you have some relation between the columns, it will be preserved after the reduction. Okay? This is the first notice. How to determine what columns to take as the basis for the column space? We said that we are going to take B1, B2, and B5, which are these guys, 1, 2, and 5. So these guys actually correspond to, I need a way to find it. When you have a large matrix full of numbers and you didn't find the relation directly, I want to find a way to get the basis for the column space.
reduction.
So then first you'll do the reduction and then you'll take the columns corresponding to the pivot columns. Okay? You interchange, you have here one step for the reduction, you have to interchange these guys. So we'll get 1, 2, 3, 5, 0, 0, 2, 2, 4, 0. Get something like this. This is the end of your reduction. And then you will find the columns that correspond to your pivots, which is 1, 2, and 5. And then take 1 and 2 and 5 from the original matrix, not from the reduced one. Don't take these guys. I'll take B1 and B2 and B5 as basis for the column space. This is very important. Okay? So if this is your matrix A, and I want to find basis for null space, row space, and column space. So to do this, first to find the null space, as we said before, you are going to solve the problem of AX equal to 0. Right? So you solve this problem first. So after reduction, you will get this matrix. So according to this matrix, what are the free variables? X2, X4, and X5. So you have 3 free variables. And then you write your pivot variables, X1 and X3, subject to the free variables. You get something like this. So this is your null space. And the basis for null space is the set of these vectors. Okay? So these guys are basis for null space. What about the basis for the column space? You look for the pivots and find the pivot columns. So you have pivot in the first column and the third column. So you'll take these guys as basis for the column space. What about the row space? How to find basis for the row space? Again, I need vectors that are linearly independent and can span all your rows. Can you get all your rows from them? You can do transpose and then do reduction again and do the same as the column space here. Is there a simpler solution without doing any reduction? From this reduction, can you read? لا. The reduction هنا اتعمل على الروز. Actually, I can take these guys as basis for the row space because these guys actually obtained from Gauss, which are linear combination of the rows. So you take these guys as basis for the row space, but these guys as basis for column space. actually one reduction, okay, and found from this reduction all the spaces and basis for each space. So this is the null space and this is its basis. The row space is the span of these rows and its basis is these rows. The column space is the span of these columns and its basis is these columns. Okay? So can you complete here the missing word? The space columns of matrix A form a basis for column space of A. The pivot columns of the original matrix. Okay. We say here if H is a subspace of Rn, then the following statements are equivalent. When we say that B is a basis for H, it means that B is a space spanning set. When we say that B is a basis for the subspace, it means that it is the أو a maximum minimum spanning set. مش كده؟ أنت ممكن تسpan more than these vectors, but this would be the minimum spanning set. B is a space linearly independent subset of H. Maximum or minimum? أكتر حاجة تقدر يبقى دول the maximum linearly independent subset of H. Okay. Lecture اللي جاي إن شاء الله بقى نتكلم على الدايمنشن والرانك إن شاء الله. Okay. شكرا.